So here's a starting point. In discussions of the quantum measurement problem, you have a quite common perspective that the situation looks something like this. There's a whole bunch of interpretations available, and we're choosing between that whole bunch of interpretations. So if in the circles I mostly move in philosophy, then that mostly tends to get cashed out as a debate between the Everett interpretation, the GRW theory or collapse theories more generally, and Bohm's theory or hidden variable theories more generally. If you hang out among physicists, perhaps more for the audience of this for this talk and this conference, it tends to be more cashed out as a debate between maybe Everett again, but maybe something like something called Copenhagen, whatever that exactly picks out, maybe some kind of physics as information or QBism. But in any case, you have this range of options available. And the idea is suggested that really all of these interpretations, or at least a large class of them, are all compatible, or at least roughly compatible, with the quantum formalism we know and love, with quantum mechanics as we use it, with the experimental data. And so if that's right, it makes the question of deciding between interpretations turn on things like what are the conceptual problems of various interpretations, or what are the attractive features or unattractive features of the interpretations. And we're all used to this game. So for instance, maybe we care a lot about how probability works. Maybe we shouldn't be Everettians because there's no good justification of why the mod squared amplitudes in the Everett interpretation are probabilities. Maybe we should be Everettians because we understand probability in the Everett interpretation better than we understand it in other areas of physics. Maybe we should reject Bohm's theory because the particles in Bohm's theory aren't doing any work. They're just along for the ride while the wave function carries on following the Schrödinger equation. Or maybe we should recognize that that's the strength of the theory because that's what the phenomenon of the observed world supervene on. There's supposedly nothing in the non-Bohmian quantum mechanics for them to supervene on. Maybe we should appeal to Occam's razor. Maybe we should say the many worlds theory is wildly extravagant ontologically, and Occam's razor says we should reject it. Or maybe we should say, well, no, the many worlds theory is the simplest interpretation of quantum mechanics, and what Occam really cares about is simplicity, and that's the reason we should be Everettians. Maybe we should have no collapse approaches because it's inelegant to add collapse to quantum mechanics, or empirically unjustified to add it. Maybe we need collapse because conceptually we don't understand why we have definite outcomes without collapse. Maybe we should reject certain interpretations because physics is supposed to be about an observer-independent world. Maybe that's got it the wrong way around. Maybe it's through understanding quantum mechanics we realize that no, physics is not after all about an observer-independent world. So there's a vast range of back and forth of this kind. And I've been an active participant in some of these back and forths, but you can kind of see why, if that's the way things are set up. Some philosophers talk about this as a sort of classic example of underdetermination, where the data just won't allow you to choose between theories. And you can also see why some people in the physics community, many people in the physics community, are inclined to say, this is, in the bad sense, just philosophy, or this is these are things to discuss in the pub after the conference, or these are just matters which don't really bear on the science. And I want to suggest that's not the right way to think about what's going on here. I want to say that the basic idea that we've got a whole bunch of different interpretations, and they're all kind of structurally equivalent, and they're all different ways of reading the quantum formalism, is just flat wrong. I think the attempt to solve the quantum measurement problem and to understand the quantum classical transition has got much more woven into the way we do physics than we can sometimes remember. It has been being woven in since the dawn of the subject. It's been woven in a lot more in the last few decades with the rise of things like decoherence theory. And so there's much less separation than it looks between the interpretation of the formalism and the formalism itself and the way we use the formalism. And I want to distinguish effectively sort of three ways we try to do quantum mechanics. And I won't say interpret because this as much applies to the first order question of how you're doing your physics as to the interpretive question of what sense you make of it. And here are my three ways. There's the modificatory way, which basically says the quantum formalism is not fit for purpose, we must change it. we must add new equations or new variables. We need collapse rules or hidden variable dynamics or things of this kind. So the modificatory way is the way of Bohm and the way of GRW. There's the operational way, which basically says, the way quantum mechanics is it's about preparing systems, evolving them, and then measuring them. And while the evolution part of that story, the dynamical part, is internal to quantum mechanics, the preparation and the measurement are external to the quantum formalism. Quantum mechanics is, at least in large part, a tool that connects claims we make in a non-quantum language of preparation and measurement. This is the way of Copenhagen. This is the way of QBism. And then there's a third way, the decoherent way. Everything is unitary. Lab processes are just physical processes. The quantum classical transition is simply a process of dynamical emergence. It's unitary quantum mechanics all the way out. And of course, the decoherent way is the way of Everett. I'd like to claim some deep connection to sort of various kind of traditions in my appeal to these three ways or something, but the truth is I've just been watching a lot of Kung Fu Panda with my kids at the moment, and I picked up that style from them. So what I then want to argue is that actually the modificatory way of doing quantum mechanics and the operational way of doing quantum mechanics don't actually let us do quantum mechanics. And I don't mean they let us do quantum mechanics in a philosophically unsatisfactory way. I mean, we can't actually consistently and systematically use those approaches in a really wide range of quantum mechanical applications. Whereas we can use the decoherent way in basically every application of quantum mechanics I know. That doesn't make it right. That's compatible with the idea that there's simply no way of making sense of the decoherent way of doing quantum mechanics, that it's inexplicable in some sense, that there are philosophical or conceptual reasons it cannot be true. It's to say that at the moment, that is the only way you can do quantum mechanics. And so if we were to decide to reject it, notwithstanding that, it would be a case of rejecting our very successful physical theories on purely conceptual grounds, something for which there is very little precedent. Okay, let me cash out those claims. And inevitably, given the format of the conference and the limitations of time, I'm going to be a bit Parisian fast in some of this, and I'm happy to defend overstated claims in the question period. I sort of feel, at least for those of you in Europe, to keep you awake at 27, then I need to make outrageous and overstated claims that you can wake up and think are terrible and fight back against, rather than nuance it too far. So that's my apology in advance. So let's talk about the modificatory way first. I suspect I'm preaching to the converted of this audience, but still, here goes. Oh, I left that in for earlier. Sorry, I think I meant to put that in earlier in the comments as to why physicists don't think there are other things to do. So here's a starting point for thinking about why the modificatory approaches, and to a significant extent as well, the operational approaches, actually don't really engage that well with the quantum theory we have. The quantum theory we have is not just one theory. When we talk about quantum theory, it's not like talking about electromagnetic theory or the theory of the hydrogen atom or something. Quantum theory is a big framework, an abstract general way in which we can write down a very large number of specific theories. So for instance, some examples of quantum systems are the qubits and spin systems that we discussed in very abstracted ways in quantum information, the harmonic oscillators that everyone studies in their first quantum course, both as abstract systems and as concretely realized things in various lab contexts. The systems of distinguishable spinless point particles that you get at if your first approach to quantum mechanics is through the Schrödinger equation in the differential equation sense. The systems of nucleons and electrons that we study in atomic chemistry, the vibrational modes in crystals that we study in solid state physics, the fluids and superfluids we just study in other bits of condensed matter physics, the field theory realm of quantum electrodynamics, and of the standard model of particle physics. That's scarcely exhaustive, scarcely anything like exhaustive, but it demonstrates it's these theories for which the concrete empirical evidence exists. It's quite difficult, I don't want to say impossible, quite difficult to test quantum mechanics in the abstract. It's possible to test various quantum theories, and it's possible to demonstrate that certain phenomena are going to be really hard to accommodate in any quantum theory. But most of what we're doing concretely in setting things up and testing and using the theory is using quantum theories rather than simply the abstract framework of quantum theory. And I want to claim that actually is only a good fit to the way we do quantum mechanics in the decoherent way. The operational way of doing quantum mechanics tends to be pretty concerned with what you might call the abstract framework of quantum mechanics. Hilbert spaces and system compositions, and maybe in a very abstracted sense, qubits, and the Schrödinger equation in the abstract H is an arbitrary self-adjoint operator way. The modificatory way is normally about trying to modify one theory. And usually the idea is that the theory that's being modified is the most fundamental theory there is. And since we don't have the most fundamental theory there is, that's always going to be a fiction. In practice, the fiction is quite extreme, and the most fundamental theory we have is fictionalized to be non-relativistic point particle mechanics. But in any case, the idea is something like that we're going to modify a particular quantum theory rather than the general framework of quantum theory. On the decoherent way, it's a kind of recipe. It says, okay, this is how we do any given quantum theory. But why does that matter? Well, on the modificatory way, let me pick, avoid disappearing, let me pick the example that I started my title with. So yeah, this is perhaps just that I miss being in California, but why is, or maybe it's because I have a 5-year-old, but in any case, why is the sky blue? This is kind of one of those classic simple questions, and as anyone knows, if your 5-year-old asks you why is the sky blue, what you have to do is give them an extended lecture on resonant modes in atomic physics, and then discuss the way in which those resonant modes couple to the excitations of the electrodynamic field when it's quantized, and then you need to discuss the wave-particle duality that lets you interpret those excitations as photons. I don't really understand why everyone thinks this is such a gotcha question. But in any case, how does that explanation play out if we're taking the modificatory way? Well, it's not kind of straightforward. Because if you look at the story we're doing, it's a very hybrid, very non-fundamental physics. We use non-relativistic quantum mechanics to work out the resonance frequencies of the electron clouds. Then we talk about the coupling of non-relativistic quantum mechanics with QED to discuss how it connects with light. We're using various different bits of quantum theory in various rough and ready ways. We're using it, incidentally, in a way that very much treats the quantum language as descriptive or representational, as philosophers put it. We use terms like electron bond, we talk about photons, we talk about scattering. We're talking about all the various quantum bits as if they're bits of a physical theory. And then we get out of the theory some more bits that are sort of laden with theory, like in this case, claims about the scattering frequencies of light. So to make sense of what's going on there, what we need is a way to make sense of various different bits of certain quantum theories applied in different places. And we need to make sense of it, not in a way that's translated directly into a language of observation or into a language of, say, what Bohmian particles are doing. The language continues to be very laden by theory, in the philosopher's term. And more directly and concretely, of course, the language is full of field theory and full of QFT concepts, which are very undermodeled in modificatory approach to quantum mechanics. So I kind of leave as a placeholder that I think this kind of account of what's going on is hard to make sense of, even on the operational view of quantum mechanics. But I'll just double down now in the fact that the no modificatory approach we have to quantum mechanics is remotely shaped in the right way to handle this kind of situation. They're mostly not well shaped to handle the idea that we have lots of different theories at different levels. And more concretely, none of them know how to handle quantum electrodynamics, let alone further development of field theory. And although quantum electrodynamics in a certain sense is relativistic quantum theory, pretty much any phenomenon we run into in quantum mechanics at all is in some sense, if you want a full analysis of it, using quantum electrodynamics. So I want to claim that, this is a comment to philosophers, that this, I want to claim that there's a vast class, arguably a total class, but a vast class of ordinary quantum explanations that we can't do modificatory. We can't explain the color of the sky, but we also can't explain the color of metals. We can't explain the conductivity of metals, or the BCS mechanism for superconductivity of metals. All of these things you can do a lot of in non-relativistic quantum mechanics, but actually it's only when you start coupling it to electromagnetic fields, including time-dependent electromagnetic fields, you get the full content. More esoteric levels, it doesn't explain the Higgs mechanism, doesn't explain the spectral lines of hydrogen, which again is a hybrid coupling problem, or the spectral lines of helium, or the spectral lines of anything else. Doesn't even explain the two-slit experiment. The two-slit experiment uses photons. And a proper analysis of the two-split experiment, if you want to understand all of it, is again going to be complex and hybrid. So right at the minute, our modificatory strategies are not ways that we can do quantum mechanics. The best we could say of them is that they are strategies to try to come up with new theories. And this is, I think, the response you tend to get if you ask advocates and defenders of these kind of approaches. They'll say, yeah, we're working on it. And we've got some interesting preliminary ideas in the case of quantum field theory. To which I think the response is, great, good for you. But we seem to change the subject, because where we came into this was we said there was a quantum measurement problem, and that means we can't understand how to do quantum mechanics. And if what you're actually saying is, here's my exciting research program for doing new physics, then that's great. And if further than that, you want to say, well, we'll have to do that research program for new physics because we don't think our old physics is conceptually satisfactory, then again, great. But that doesn't help us with the problem of saying, nonetheless, if we don't want to just give up on quantum mechanics, stop doing it and spend all of our time developing the Bohm theory, we actually want to carry on calculating colors and spectral reflectancies and so on. We can't do that inside the any modificatory framework. We are very, very far from what philosophers call underdetermination. We are very, very far from having modificatory alternatives that can actually reproduce what quantum theory does. There's also a sort of subsequent modifier response, which says something like, well, what you expect, there's only a smallish number of people working on these programs. They're not going to have got very far. And my sort of feeling there is, well, fair enough, but your failure to recruit people into your programs or get grants for your programs is perhaps very unfortunate, but again, not that salient to the question of how to interpret quantum mechanics. But that's an unkind observation. Okay, let me talk, perhaps this is more salient to this audience. Let me talk more about the kind of ways in which a sort of operational Copenhagen-style approach to quantum mechanics, again, just isn't sufficient to make sense of the quantum mechanics we do. And the starting point here is that, you know, a common theme of these sort of general approaches, and again, I'm generalizing a bit, but the common theme is something like the observer, the measurement process, plausibly the state preparation process. It's not quantum theory's job to describe that. That's outside quantum theory. And so we ask ourselves, in that case, if these measurement devices are not described by quantum mechanics, well, where do they come from? And here's one answer where they came from. So let me skip across that time. Maybe we find them scattered across the desert. Maybe we went out into the desert and we found a large number of boxes which were completely impenetrable, which had stamped on them, I measured this alpha joint operator. And further across the desert, maybe we found a bunch of other devices, and these devices spat out quantum particles when you press the on button. And these devices were stamped with a label saying, I produce states in quantum state something. Maybe we found these measurement devices, and we found these preparation devices, and we connected them together, and quantum theory was this wonderful theory we found of how to link the measurement to the preparation to the measurement. Well, I studied theoretical physics and moved into philosophy of physics when theoretical physics seemed too practical. I would not pretend expertise in how actual experimental physicists do physics, but I've talked to some of them. And my understanding is this isn't actually where measurement devices come from. What I learned from my experimentalist colleagues is it's more like this. We actually build measurement devices using physical principles. We understand how measurement devices work. We construct them, we set them up, we develop them, and they're bits of kit that do what they do because the laws of physics say they do. In which case, which physical principles? Not quantum principles, presumably. Bohr had a perfectly good answer to this. Bohr was as Peter Bohm was reminding us, Bohr was a deep and serious thinker. Bohr's answer was that the principles are classical principles. For Bohr, the quantum classical separation was a separation that we needed because quantum theory was not in the business of describing the world, but classical theory was. And although I'm no historical scholar of Bohr, I think it's natural to read a lot of Bohr's very concrete, classically constructed and discussed devices in his various thought experiments and his famous exchange with Einstein as illustrations of how this kind of must be concretely realized in the language we have, press was supposed to go. Anyway, yes, so the measurement devices we build these days involve principles that vastly transcend anything you'd call classical physics. I mean, the picture I've got here, which I just pulled off the internet, to be honest, but the picture I've got here, I think, depicts a laser. A laser is just one example of a physical device that employs quantum mechanical principles in its operating. Anytime we use superfluids or superconductors in our experimental work, we're appealing to quantum physics to get our full understanding of how it is they work. Anytime we use computers as part of the processing of our experimental data, we're appealing to quantum mechanics in doing that. The separation between the classical language in which we discuss experiment and the quantum language in which we discuss the relations between the experiments, or between the inputs and outputs of the experiments, if that dichotomy was ever valid, it certainly isn't valid now. Again, in the jargon of philosophers, experiment is very thoroughly theory. There is not a clean separation into experimental talk about which we can have one attitude and theoretical talk towards which we can have another attitude. And as a philosophical digression, this actually matters in the debate about the philosophy of quantum mechanics, because it's a general theme that came up in the philosophy of science mid-century. We often talk in these sort of discussions about realism or versus anti-realism. Sometimes we talk about the fact that we want a realist interpretation of quantum mechanics because it's the job of science to tell us what the world is like. And sometimes we find the idea that the only thing that's wrong with various approaches to quantum mechanics is that they're not realist in this sense. I touched on that in my earlier examples. And sometimes we get the idea that generally what's wrong with not being realists in science and what's wrong with being instrumentalists in science is just that it's somehow got our goals wrong, that we should be, that we somehow immoral to only use science as a device to predict the results of experiment. But again, simplifying a history, the reality is that the reason why instrumentalist approaches in general philosophy of science fell from grace has much less than you think to do with a feeling that instrumentalism is asking the wrong questions, and much more of a feeling that it doesn't work even in its own terms. And again, it doesn't work because it relies in most of its forms of some ability to separate out what can be said in the language about observations from what can be said in the language of theory. And doing that just doesn't consistently seem to be possible. And when we try doing it in quantum mechanics, we likewise find this. We don't find that we can excise the quantum language from our discussion of the measurement devices. The systems are quantum all the way through. So that's one major problem with trying to do operational style approaches in quantum theory. It struggles with actually having a language to describe the very experiments we're doing. And I think for that reason, it's probably not surprising that that approach to quantum mechanics gets a lot of its strongest adherence in places where we abstract all of that away. In the kind of quantum information context, where we genuinely do treat measurement as primitive and preparation as primitive, and we do just stipulate Hamiltonian arbitrarily, then at that level of abstraction, you really can do quantum mechanics without any of these kind of analyses. But when you try to move away from the abstracted space of quantum information to any concrete quantum theory, including attempts to realize quantum information systems, things get messier, and we're no longer allowed to avoid applying quantum mechanical principles to the very machinery we're using to test these theories. So that's one big class of problems with this kind of approach. There's another class, though, which I sort of touched on in the Sky example earlier. And that other class of problems is that this kind of stylized paradigm where I'll prepare a quantum state, I'll evolve the quantum state, I'll measure the quantum state, really isn't suitable to handle more than a small and stylized fractions of the applications you make of quantum mechanics. So let me demonstrate. So for instance, suppose you just sit and watch a Geiger counter. Suppose we just, I've got some radioactive material and I'm sitting back and I'm observing. Unitary quantum mechanics has no problem handling this. The system evolves gradually into a superposition where it'll be a superposition of me observing no click, or let's keep me out of it. It'll be a superposition of the Geiger counter clicking and a range of states in all. I'm sorry, I'll say it again. It's a superposition of the Geiger counter not clicking and a range of states in all of which the Geiger counter has clicked and where it's clicking at a continuum of different times. And if I want to sit and watch Schrodinger's cat in sadistic fashion, then the superposition will be a superposition of me seeing the cat continuing to be alive and a vast range of different terms where I see the cat dead at various different times. It's perfectly analyzable, but it's not very well suited to the kind of, well, now I've done an experiment and I've stopped, because there's no particular sharp time when the process stops. I think there's a reason why actual discussions of Schrodinger's cat very rarely, when one goes into the technical details, very rarely use Schrodinger's own example of the decaying particle. They normally consider a discrete click so that we can abstract away these kind of issues. A second example. I mean, suppose I just want to know what actual objects do. I mean, we could talk about the color of the sky as an object, talk about the colors of metals I mentioned earlier. I could talk about all these issues of conductivity or why neutron stars do what they're doing. Again, what we seem to be doing here is just using quantum mechanics and using, necessarily quantum mechanical features of quantum mechanics, like the relativistic feature, the features of relativistic quantum mechanics that say why gold is gold, or the parallel exclusion principle features that tell us why neutron stars and white dwarfs are stable. We're using those features to describe ongoing systems that we didn't prepare, and that we haven't measured in any particularly definite and discrete way, that are just sort of out there getting on with it. You could say the same about atomic chemistry, you could say the same about the periodic table. Now it's clicked very fast here for some reason. You can say the same about places where we use quantum processes as bits of a larger story. So we have a theory as to how the sun works. It's pretty well confirmed and it's substantially quantum mechanical. It relies on our quantum mechanical understanding of nuclear fusion in the core. It relies on various quantum mechanical theories about how light manages to diffuse its way out through the star. We use quantum mechanics to work out diffusion factors of light in the stellar medium. But we don't test those things simply in isolation. We didn't kind of drill down to the core of the sun and pull out a chunk of it and check whether it obeyed the principles of nuclear fusion. The way in which testing our theories of something big and complex like the sun works is that they make a whole bunch of predictions and we see how good the overall fit is. So among the various fits there, if you want, our theories tell us various things about how the sun was burning brighter at earlier times in history, and how it has certain sort of fluctuationary periods. And the reason we think it's burning brighter at earlier times in history has to do in large measure with the way in which the temperature in the core changes and the way that plugs in to the temperature dependence of the cross-section for nuclear reactions, which is a quantum mechanically calculated feature. How do we test that directly? Well, among other things, we can look at sort of paleoclimate data and fossil record data and get various inputs as to what they tell us about the intensity of the sun at various earlier geological epochs. But it's pretty weird to say that my best fit in a paleoclimate model counts as a quantum mechanical observation of the interior of the sun. And of course, perhaps most famously, the one everyone knows about, the cosmological cases. Here's everyone knows this picture, the lovely fluctuations across the night sky that Planck and Fermat pick up. Those fluctuations, of course, are quantum mechanical in origin. At least we have strong reason to think they're quantum mechanical in origin. Does the satellite count as a measurement of the microwave background radiation in the quantum mechanical lab sense? It seems difficult to sustain that, not least because those measurements are only part of the very wide range of data we have about the inhomogeneities of the early universe. Other aspects of that evidence comes through our cold dark matter modeling of how large-scale structure formation formed. And again, we have a lot of different pieces of the jigsaw that all fit together and support the overall cohesion of the theory. And again, one can handle that fine in the language of decoherence. We can understand perfectly well that those microwave fluctuations are very thoroughly decohered, and as such, one can extract information about them highly redundantly, so that there's no problem with the fact that we got information out of the fluctuations by looking at the night sky, and weren't therefore thereby able to get more information out by looking at different bits of the night sky. But again, the format of doing this is way outside anything that you can do just by saying, what I'm doing is quantum theory in the lab, what I'm doing is preparing my system, evolving it, and measuring it. So I want to say that when we actually look at the way in which quantum theory has been used in the 20th and 21st century, if we look at the shape of their applications, if we get outside either the very stylized world of non-relativistic point particle mechanics, that's the main focus of attempts to modify quantum mechanics, or the differently equally stylized abstracted world of quantum information simply in its primitive form, in its sort of uninstantiated form. If we get outside those contexts and look at the range of things we really use quantum mechanics for, we just don't have a way of doing it that isn't unitary quantum mechanics. We don't have a way of doing it that doesn't help itself whenever it needs to the ability to expand the system, to move to the church of the larger Hilbert space, as quantum information theorists often say. The church of the larger Hilbert space, if you like, is the low church version of the Everett interpretation. So I conclude from that, if what we want to do is see our way to the next theory, the theory that comes beyond quantum mechanics, then maybe these various modificatory strategies are really going to help us. If we want to see our way to the physics that's beyond quantum physics, then maybe these attempts to look for hidden variable underpinnings of quantum mechanics, or to look at the operational axioms on which you could rebuild quantum mechanics, maybe those things are going to be the route we go. I don't know. It's folly to speculate on which interesting ideas developed by smart people are going to lead to the physics of tomorrow. But if what we actually want to do is keep doing the physics of today, which is quantum physics, if we actually want to be able to carry on using quantum physics in the vast range of places we use quantum physics, including the many, many places where specifically quantum aspects of quantum physics are doing the work, from superconductors to neutron stars, then the only way we currently know how to do it is Everett's way, the way of unitary quantum mechanics and the way of decoherence. I mentioned in the beginning the temptation by many physicists to say, shut up and calculate, and the sort of feeling from many people, including advocates of the Everett interpretation, that this advice somehow is a dismissal of all of the interesting work that's been done in the foundations of quantum mechanics. And I think much of that is true, but at least to some extent, you can see it more as an internalization of the lessons that we've actually learned and that have become embedded into physical practice about how to do quantum mechanics. If the motto is shut up and calculate, a slightly more detailed version of it might be shut up and keep using the Everett interpretation to calculate. Now, I don't think people should shut up. As a philosopher, I'm fascinated with the question of whether it's right that unitary unmodified quantum mechanics a la decoherence is compulsorily to be understood in a sort of realist many worlds sense, or whether there are more finessing ways of doing it, whether Wojciech's or Carlo's or Jim Hartle's or any of these routes. And I'm fascinated about whether there are differences between ways of reading unitary unmodified, include the observer quantum mechanics, that count as genuine differences of a physical theory and not just a sort of different general attitude to the philosophy of science. Whether there's a way of saying, well, I don't regard Everett branches as real world, but I'm still going to use unitary unmodified quantum mechanics, that isn't just the same as saying that I'm going to carry on using any other scientific theory, but I'm going to draw back from believing all of its claims. So I'm fascinated by that question. I'm fascinated by whether indeed Everett can inform deep philosophical conundrums like how to think about probability. And as a physicist or lapsed physicist, I certainly think that we shouldn't be complacent about the truth of quantum mechanics, and that the increasing attempts to probe our theory in regimes where we haven't yet looked at it is really, really important. It might lead to something enormously significant. Clearly, as Wojciech was reminding us, a discovery of a way to change quantum mechanics itself would be the physics discovery of the century. But equally, I don't expect it to happen. I don't see any particular evidence that the unitary way of doing quantum mechanics is problematic. And while I think quantum mechanics is fascinating, a lot of what I think is fascinating about it is the particular quantum theories I can do in it. If you like, I find quantum theories fascinating, but I find superconductivity fascinating and superstrings fascinating. And so to me, it's really important that we have a way of doing quantum mechanics that actually lets us do all of the quantum mechanics we have. And that way is basically the way that developed from the founders of the theory, from Mott and Heisenberg and von Neumann, but which, more than anything else, bears the name of Everett. And I'll stop there. Thank you.
Thank you so much for your talk. Then we've arrived for the Q&A session. I will just enlarge the screen. I'm not entirely sure who was first. I think Francisco Pipa was first. If so, please go ahead and ask your question.
I'm not sure if my question is appropriate because I think that you didn't use this terminology in this talk, but in your paper, in the original paper, you talk about the representationalist strategies and the non-representationalist strategies, and you say that Everett is a representationalist strategy, right? Mm-hmm. Now, I was always curious about what that meant for you, about how can you read from Everett representation? Is it surely not like Sean Carroll's way of looking at representation? It's something much more, maybe more less literal, right? And I wonder if always puzzled me this ambiguity in the word representation that kind of never made sense for me in this. But I see that you in this talk, you didn't use the word representationalist.
I shift the way I give this sort of talk depending on the audience, but I'll respond back to the idea. So the sense in which I think the theory is representationalist kind of goes back to what I was saying earlier in the talk about my specific quantum examples and how the way we talk about, say, the color of the sky involves using very representationalist language to talk about the various bits of the quantum formalism, like here's the emission rate, here's the here's the bond strengths, here's the photon being scattered, all this kind of thing. How do I get that out of Everett? Or how do I get this out of unitary quantum mechanics? I think the thing to be clear about is that it's going to be extremely difficult to get any representational content out of abstract quantum mechanics. Just as it's extremely difficult to get any representational content out of abstract classical mechanics. I mean, the abstract phase space framework is just as apt to represent the geometric dynamics of vacuum general relativity as it is to represent a ball on a spring. The amount of detail, there's not no detail coded in the abstract structure of phase space, just like there's not no content coded in the abstract structure of Hilbert space, but there's very little. Most of the content of our quantum theories, just as our classical theories, comes from the specific dynamics, system subsystem breakdowns, relation to space-time, symmetry structures, and so on, that you'll find in any of our particular quantum theories. So don't ask me what the representational content of Everett is. If we want to have a conversation about the representational content of the electroweak sector of the Standard Model, a la Everett, that's the kind of conversation I think one could have. Now, Sean's trying to do something more ambitious than that. Sean's trying to say, well, suppose all you had was the Hamiltonian spectrum and nothing about, say, system-subsystem structure or the relation between observables and space-time regions. How much can we recover from that? And I think that's a terrific project, and I have no idea where it will go. I want to resist the idea that it's just what we're forced on if we want to interpret Everett.
Yeah, thank you.
Okay, then again, I'm not entirely sure if the hands that I can see are kind of in chronological order, but I think Maria Foliaris, if you want to ask a question, please go ahead.
Yeah, thanks. Thanks for the talk. So my question, I was wondering if the Everett interpretation is the only one that kind of makes sense on its own terms at the moment, then why do you think that the Copenhagen interpretation is still very widespread? If you kind of ask the average physicist what interpretation they ascribe to, like, do you think it's a problem of a difference in philosophy or something like not knowing, just not being aware of the arguments? And
I think the answer is I don't think, if by the Copenhagen interpretation they mean what Bohr said or what Heisenberg said or what Dirac and von Neumann said, I don't actually think they do believe in the Copenhagen interpretation. It's not what they're using in their physics. I think what physicists mean when they say the Copenhagen interpretation is something like what I'm currently doing and getting on with. But I think that the Copenhagen interpretation, understood that way, is extremely Everettian. I think if you look at how people are using, Simon reminds me in the chat that, language like complementarity or the uncertainty principle, you just don't see this much in modern use of quantum mechanics. And that's changed even over my professional career. And I remember teaching often lags research. And as a physics undergraduate in the 90s, a lot of the lecturing, particularly from more senior people, would be all about these kind of classical analogues and various uncertainty-based arguments. And that kind of style of doing things has passed very substantially out of the research literature and to a large extent out of the teaching literature. So I think if you want, inevitably and not unreasonably, most physicists using quantum mechanics are not thinking that much about how what they're doing connects to the foundational discussions. And so when they say, I believe in the Copenhagen interpretation, you can't really work out what that means until you actually look at the way they do quantum mechanics. And the claims I'm trying to make is that in most of these spaces, the way they're doing quantum mechanics is insofar as it matters at all, is Church of the larger Hilbert space, is apply quantum mechanics to the system, the measurement systems and the devices you're building whenever you need to.
Okay, thanks. And what do you think it would take then because I guess it seems like lots of people are using the Everett interpretation in a way without really realizing they are, but what would it take would it just be a question of educating more people about it? Do you think that would persuade people to accept that they are using it?
I don't know, but in some ways I don't put a very high burden on trying to persuade them. I mean, I'm not sure except as far as people are getting confused. It's not for me to dictate how professional physicists should do their work. I think one of the virtues of, I think here's a small bit I'd say towards that. In this talk, I'm being a bit sloppy as a distinction between, well, I suppose low church and high church Everett. If low church Everett means just do unitary quantum mechanics, and if high church Everett is more willing to help itself explicitly when it wants to a language of decoherent branches and multiplicity. I think sometimes if one's only low church Everett, one can get confused. One can end up with a slightly tangled language in various places. You can see this a little bit in some of the discussion of black hole information loss, actually, where occasionally some of the material there blurs into measurement problem issues. So insofar as I would think there's an agenda worth doing there, then I think the language of Everett is useful the more explicit many worlds language of Everett is often a useful way to avoid certain confusions. And I suppose if I wanted to persuade physicists to take it more, to use that language more, that's probably the route I take. But I'm not that moved by trying to persuade them. If they're actually doing unitary quantum mechanics, then I'm happy for them to get on with it.
Mm-hmm. Great, thank you.
Thanks for the question. Then Jos Ehrlich.
Yeah, thank you for a very nice talk. So as a modifier myself, I come from the high energy theory and quantum gravity world, and I'm a modifier, so I'd like to express some sympathy for the modificatory approach, if I may. So it seems that your point of view is predicated on unitary quantum mechanics as being a successful program. And in quantum gravity, I would argue that it's certainly not, or at least the combination of the ideas of unitary quantum mechanics with general relativity, that combination has not been a successful program. So something has to give. And if you take the point of view like I do, that it's quantum mechanics, the rules of quantum mechanics that have to give, then it really seems worthwhile to me to consider the various pictures of quantum mechanics as distinct, because a modification of, for example, Bohmian mechanics will lead to a new quantum mechanics, which is not equivalent to the other pictures of quantum mechanics, like the Schrödinger picture or the Heisenberg picture, or the functional integral for that matter. So from that perspective, I suppose I'm also taking issue with your distinction of future physics and current physics, because I think of quantum gravity as a subject of current physics. And in order to do quantum gravity, I do need to modify my perspective on something, and I take that to be quantum mechanics. I'm just curious about your thoughts.
Yeah, I mean, I'm not unsympathetic to a lot of that. I mean, we could have a different discussion about how much progress or lack of progress we think has happened in unitary quantum gravity, but it's at least reasonable to say that we should, given the absence of empirical data there, that one should be looking at other routes. And I don't have a problem with that at all. What I roughly mean by future physics versus present physics is not sociological. It's more something to do with where are the places where we have robust and thorough empirical confirmation, versus where are the places that we don't really have that, where we have fragments of most of the empirical data. And I mean, I don't really have an agenda to push against modificatory approaches to quantum gravity. Insofar as I were to, the only thing I'd say is that I can't speak for your own work, that some people in this space are a little too quick to say, in my view, to say something like, well, we have these relatively toy models of Bohm or GRW that work for these particular stylized non-relativistic systems. So now we're going to try to quantize gravity and not stop off and try to see how we can understand, BCS superconductivity or the color of the sky or something. I mean, it's difficult to guess where progress will go, and so I don't want to say no. Actually, we won't reach some brilliant end run around the on-path of quantum gravity by trying this. So don't at all take my comment as pushing against that kind of research program. I would, closing the circle to the beginning of the talk, I would want to push strongly against the way some advocates of Bohm's theory or the GRW approach will sometimes want to say that this at the moment is a satisfactory alternative to quantum mechanics. I think that you see that less in physics circles, but sometimes in philosophy, and I think that's often just a little underinformed about the sort of spread of physical applications.
Take your point, thank you.
Thanks for the question. Then I think we have time for a final question before we end this talk and then go into the break and discussion session. I see Scott Aronson has a question. Please go ahead.
Oh, okay, great. So I was wondering if you could think of any example of a physicist who said, well, I wouldn't otherwise have accepted the Everett interpretation. I didn't like it or whatever, but I was forced to because of the applications to QED, or because of field theory applications. Like, has anyone ever made that move?
Well, I can think of a ton of people who've used Everettian moves of various kinds in this space. Can I think of ones who've been dragged into it kicking and screaming? Not really, but then of course you're not going to see that in the paper. And I think in particular what you have, I mean, it's a really good question. I'd like it'd be nice to know. So other people here study this stuff better than I do and might have a good answer. I think what you actually see is a lot of the earlier applications of unitary type methods. I mean, I think of the Zeno effect discussions in the 80s, for instance. It's very much getting its work through unitary technology and through expanding out to include the measurement system and not using a collapse rule. But people are kind of avoiding using the word Everett or many worlds. Sometimes they'll cite Everett, but they won't use many worlds language. I think partly that can personal distaste, and sometimes it can be a sort of fear that if you put these foundational things into your papers, you can get into trouble for it. And I always suspect that to some extent, some of the language of the Church, the larger Hilbert space, was used by some advocates of Everett as a kind of plausible deniability way of committing to the Everett interpretation, kind of like you get in underground political movements sometimes.
Thanks.
Great. That was actually a bit briefer than I thought, in which case, maybe as a final question, Simon Saunders.
Right, thank you. Well, this isn't going to be a hostile question now, is it? But at the same time,
It can sometimes be the worst question, Simon, as you well know.
But I want to try and channel Tim Maudlin a bit because he's not present today. So I think Tim's point of view would be that, well, sure, quantum physicists routinely use unitary quantum theory, but they illegitimately have in mind a sort of inarticulate but nevertheless relevant hidden variable theory, something like that. And that illegitimacy is what enables them to sort of do significant and empirically relevant work in quantum theory, but that it is illegitimate and not honest. And if they are to get honest about it, then they would have to be driven to something like pilot wave theory or to reevaluate what it is that they're doing. So I think Tim has said things like that before. I just wonder what you said back to him.
Well, I mean, let me not put words in Tim's mouth, so I'll just respond to the hypothetical person you're considering. I think you have to do the work. I think you have to look at the actual way people are using the quantum mechanics here and say, this is the place where the illegitimate hidden variable assumption was being testily made. And I don't really see that. I mean, I mostly just see a kind of intuition as to how it should work. I see a lot of reconstruction from undergraduate textbooks. I see a lot of people who just wrongly assume that what's going on is every now and then some people explicitly apply a von Neumann collapse in their calculations and write it down. I think it's a good project to look, as this is more of a sort of philosopher's way of thinking about it, it's a good project to look at extant quantum theory as it's used and try to reverse engineer what's the rational reconstruction of what the quantum theory actually being used is. I think that's a much more sensible strategy for philosophers looking at quantum mechanics than to go to canonical textbooks, which are often out of date, often have an axe to grind, as Kuhn taught us, are not always the right way to see what the science is actually saying. I wouldn't claim to have done that in a systematic fashion. I've read a lot of physics of various kinds, and it's possible to read pretty much all of the quantum physics I read out of decoherence. Does that absolutely rule out the way you can't read it otherwise? I'm not sure. I think the nearest I'd say towards the hidden variable point is that I think physical practice is probably, as you know, I've said something like this before, physical practice is probably better characterized as unitary quantum mechanics in a sort of tacitly decoherence framework, with a kind of inchoate shift in your interpretation of the quantum state between the macro and micro way, so in the macro way, in the macro context, you talk about probability and alternatives, and in the micro level, you talk explicitly representationally. That kind of talk isn't doing a lot of work. It's the kind of, going back to the earlier question, that's some of the place where I think some of the confusion comes in. And I think, again, if I was just reconstructing what a physicist is doing, it's closer to that than it is to a kind, for many people at any rate, than it is to a kind of completely unapologetic many worlds style of Everett. But I don't think it's anywhere near a tacit hidden variable theory. I just don't see how you can look at the concrete uses of the theory in actual physics that isn't your reconstruction of some undergraduate textbook in the 1970s and get that conclusion. Here is why I'm not responding to the actual Tim, because you may not be doing that. But I think the person you're describing needs to do their homework.
I mean, just to have a quick comeback, I think the archetypal place at which it seems that working physicists seem to be talking about a hidden variable theory is when they talk about uncertainty in position of the particle. Is that, well, it has a position and we're just not sure what it is. It's that sort of talk, I think, that, but I think that sort of talk doesn't actually go that deep. So
I want to see an example of that. I would be interested to see an example of that as load bearing. And I'd be fascinated to see an example of that that's load bearing and postdates the Clinton administration.
Yeah, no, I agree.
Okay, then thank you very much for your question. And thank you again, David Wallace, with a wonderful talk. I invite everyone to join me in clapping a final time.